input some data, execute the instruction, and write some data. Right, that's sort of the typical pipeline. The clock is connected to everything. You can't do anything without the clock. And so what you can do is you can add a register to the clock. You can connect it up with some wires and count clocks, right? And then do readback out of that register. This is notional. This is not exactly how it's done, but it kind of gives you the right frame of mind to think about the problem. So what if you want to have that one register, that one counter connected to a bunch of other things? Well, you could then run some wires to other things. So in the previous slide, we had the counter connected to a clock, but we could have it connected to the caches. We could have it connected to the instruction pipeline. We could have it connected to the this instruction branch predictor thing, and we could do that. But then we have wires running all over the silicon, and that's could be an engineering issue. But the point is that we could imprint, assuming we could run wires like this. The point is that through the configuration register, we would say, hey, I'm interested in collecting data from the caches, component. Okay, begin, and then the counter runs for a while your program runs, and then when your program's over, then you read back, whatever values in the counter, right? And so that's basically how it works. And so you actually don't want to run wires all over the chip because that's a bad thing. That getting chip layouts a black art in and of itself. And so the closer that you can have components to one another, the better off you are. And so here we have, I'm not sure what's up with, there we go. All right. So, here I have a control register and a program, monitoring counter unit located next to the caches, and it can also talk to the instruction pipeline. There's another one over here, PMC2, that can, collect. It can count clocks, and it can also count what's happening in the pipeline. And then there's PCM3, which can talk to either the pipeline. It can count what's happening in the pipeline, or it can count what's happening with branch prediction. And then there's a global control register, the one ring to rule them all. And so the name of these things, these combinations of these, control registers and program program monitor counter registers, these are known as model-specific registers, MSRs. And so if you run across that term, you'll know what it is. It's a set of registers for working with collecting hardware performance data. And so, as I mentioned, there's two types. There's a set of fixed registers that always collect the same things, right? So like, clock, for example. And then there's a set of programmable ones that you can have them look at different things, right? So, Control 1 and PMC1 is programmable in the sense that they can, look at events from the caches or from the pipeline. So pros and cons of working with hardware performance counter data. So you can get a lot of really highly detailed information about your program's performance, just a ton of information. There's a lot of different information from memory events to vector instructions versus scalar instructions, branch mispredictions, on and on and on. I mean, there's like hundreds of potential events that you can monitor. There's a bunch of different types of tools that you can use to collect this information. The information that you're getting with hardware performance counters is very low level. It's what's happening at the CPU level. And so there's some cons here. So one is that there's a lot of detail, and it's easy to get lost in the forest for the trees, right? There's just so much information. Some of this information is difficult to interpret, and you got to dig up pretty detailed technical references to understand what the counters mean. Some of the counters are absolute, they're accurate. Others are estimates. They're estimates. They're not actual counters. They're estimates of what the count would be. And so sometimes these numbers are off a little bit. And so you have to look at the information and understand how the information is collected and presented, and use that background information in your assessment, when you're doing an analysis, right? So numbers you get from one counter, you may be like, I don't really believe that. I don't believe what that's telling me. So you got to watch out for that. So sometimes you're only interested in a small part of the application, so like in your coding example so far, you use that chrono timer code just around the piece of the computation that's of interest. And so a lot of these, hardware performance counter tools, you run the application from the command line, and things happen, and you're collecting hardware performance counter data for the entire application, right? So for your matrix multiply example, you would be collecting performance counter data not only for your code but also for the CBLAS verification step, right? And so the numbers that you would see from that would be inflated. It would have too much stuff in there. Because these are low level numbers, they don't really tell you anything about which line of code or which method or function or whatever in your code is the one that's taken up all the time. And you have to use a different set of tools for that sort of thing. And so we could talk about that a bit, but these hardware performance counter things are really low level things. Okay, so here's a bunch of tools for accessing and displaying information about the hardware performance counters. There's a bunch of them here. So we're actually going to use one called Liquid, which is from some colleagues over in Europe. It's actually, they've done a really nice job with it. PAPI and Tau are, a couple of the more well-established packages. Both are good. PAPI is a completely programmatic interface where you're actually having to go in and PAPI presents a low-level interface to those control registers, right? And it's okay for some stuff, but I'm not crazy about it. Tau is a little bit higher level. Tau wraps up PAPI amidst a whole bunch of other stuff. Tau is actually really useful in the sense of looking at inter-process communication stuff, right? So when you get into distributed memory computing, one of the measures that you might want to think about is how much data moves between ranks, between MPI ranks, right? And so, hardware performance counters don't really give you that directly, but some MPI shim layer probably would, right? And so Tau does that kind of thing. HPC toolkits, an up-and-comer. It's actually supported by the Energy Department's Exascale Computing Project, and so it's undergoing active development. Speedshop I know less about, but it seems to be sort of a soup to nuts profiling kind of thing. So you could actually find hotspots in your code using Speedshop. And then there's an older thing called Perf, which has been around for a number of years. I don't know much about it. I haven't used it. Okay, so Liquid. So the Liquid. CS people love acronyms, and I love this acronym, like I know what I'm doing. And so you could tell it's some Germans because they said, like I knew what I'm doing rather than like I know what I'm doing. But they laugh about that when they give their presentations. And so they're a really smart, motivated bunch of people. I really like them. Liquid's an open source toolkit and framework for collecting hardware performance counter data. You can use it on unmodified applications. And so this is actually really cool because somebody earlier in the semester was asking, can I do my coding in Python? Well, guess what? You could use Liquid with Python if you want. You could have Liquid, collect hardware performance counter data from Python, but you might be kind of hard pressed to figure out how much is the Python interpreter and how much is actual, work once it gets reduced to microcode. That's an open question. This Liquid works with serial or OpenMP parallel applications. There's new stuff on their website that I was looking at. It says that they support work with with MPI. So we may look at that. It supports most x86 platforms. It says ARM platform is experimental, as are the Power 8 and 9 and NVIDIA GPUs. But in the documentation, it says something different. It doesn't say those are experimental. And the last time I tried to use it on GPUs, I don't know, 6 or 8 months ago it broke, and so a couple of new versions have come out since then. So I need to try it again and see if it's actually working. And so there's a couple of websites that you can go and look at. One's their main, the GitHub website is the main page. That's the one to look at for lots of technical stuff. The other one is sort of the their institutional homepage, I guess. Unfortunately, Liquid is built on these MSR registers, which are accessible through a Linux kernel module, and they don't work on Windows machines because there's no MSR kernel module in Windows, and it doesn't work on Mac OS either, and it doesn't work on the VM, our VM, which is actually an Ubuntu thing, which has Linux on it, because the VM actually insulates you from the underlying hardware to some extent. So I wish it wasn't like that. And maybe we can figure out a way to make the VM do the right thing so that you can collect hardware performance count data. But for right now, this is installed at NERSC, and it works at NERSC. Okay, so inside Liquid are a couple of things. There's a bunch of command line tools, and then there's a marker API to use for instrumenting your code. And so the marker API is, you'll go in and you'll drop some marker calls to the marker code to delimit the areas of code that you actually are interested in collecting performance data for. The command line tools, Liquid Topology, prints out a lot of useful information. I'll show you in a second. Liquid Perf Counter is the main workhorse for configuring and reading out performance counters. And then there's a thing to reset the memory if you need to get cache lengths from the last level cache. So to get set up for using Liquid on Cori, you have to add a little bit to this salloc command. You have to add this --perf equals liquid to the end of the salloc thing. And what that does is that tells the Linux kernel that it's okay for you to access that information. And then once you're on the KNL node, you can load the Liquid module. Actually, you could load the Liquid module while you're on the login node, and then hop over to the KNL node, and the Liquid module will still be loaded and those tools accessible to you. On the VM, I put Liquid on there, and you can, if you do a module load Liquid from the command line inside the VM, it'll make Liquid 5.2 available to you. So Liquid Topology prints out the right thing, except it only will show one core, regardless of how many cores are on your processor. Liquid Perf Counter, some of the numbers that it produces are okay, but most are not. And so it's consider it like a useful training ground. You can play around with Liquid on the VM before you go over to NERSC. Okay, so compiling with Liquid's marker API. So I'll talk about this on Monday. So I'm going to talk a little bit about homework 4 later today, but I'm going to actually go into some detail about the code harness because it's going to look a little bit different than what we've done so far, and I want to talk you through that. Everything that you've done so far has been pretty straightforward with regard to CMake and running and that sort of thing. And with Liquid and doing parallel stuff, it can be tricky. And so I want to talk you through some stuff so that things go smoothly. So this Liquid Topology command, so I ran this on one of the KNL nodes, and I have several pages of output. So here we see, the CPU name, it's Intel Xeon Phi 7250 running at 1.4 gigahertz. There's 68 cores per socket and 4 hardware threads per core. That's a lot. And then hardware thread 0, blah, hardware thread 1, blah, so on and so forth, right? And this goes on for, 260 something lines. Right? So there's a lot of output there. Down towards the bottom of Liquid Topology, its output is telling you about the cache topology. And so here we see a level 1 cache. Its size is 32 kilobytes. And you might think, wait a minute, the web page says 64. Well, 32 kilobytes for data and 32 kilobytes for instruction. And so this 32K is for the data and data cache. I'll talk about what all these numbers mean here in a second. And then the level 2 cache, there's 1 megabyte level 2 cache and no level 3 cache on this processor. Okay, so let's look at this topology line here for a second. So the top level cache, remember that there's 4 hardware threads per core. 4 hardware threads per core. And so this says that on the first core, the threads are numbered 0, 68, 136, and 204. And those 4 threads, which live on core 1, have access to that, have access to one 32 kilobyte cache. On the next core, it's threads number 1, 69, 137, and so on and so forth, through all 68 cores. Now, level 2, it gets a little bit more tricky because and I'm going to show you a diagram here in a second. Each pair of cores lives on a tile, what's called a tile. And for each tile, there's one L2 cache. So 2 cores, each core has its own L1 cache, and then each pair of cores on a tile share a single L2 cache. And there's a bunch of those tiles on the entire processor. And so here, for level 2, we see, the first 2 cores, all those threads pile up here on, and this share this level 2 cache. So you'll see from above, thread 0, 68, 136, 204. So those 4 threads from core 0 and the next 4 threads from core 1 are all part of the same cache group for the L2 cache. Right? So that's what this says. And then the with respect to main memory, so we see total memory is 96 gigabytes, of which about 93 is actually usable. And in terms of the NUMA domain, the word NUMA domain means a processor and its associated memory. And so what this says is that there's one NUMA domain on this chip, and there's 96 megabytes of main memory attached to it. So that's one command, liquid topology. And so if you run this command on your VM, it'll show you the name of your processor, but it only shows it having 1 core. And I can't remember if the cache information is correct. I think the cache information is actually correct. So this is a handy bit of thing when you're trying to figure out how to do thread mapping, which is a more advanced topic, which we may or may not get to in this course. Okay, so liquid performance counter, the liquid perf counter, is used to read and to configure and read out the hardware performance counters. And so this is going to be the main thing that you use. And the basic syntax is liquid perf counter, and then it has a bunch of args, and then you're going to give the name of your program executable, so your a.out, and then whatever program arguments you need to run your program. And so the args that you're giving, you're indicating which performance counter group that you want to read and configure and read. You are also going to configure thread concurrency and thread affinity, which is how you pin a thread to a core. You're going to indicate whether or not you want to activate or not Liquid's marker API, and we'll talk more about that on Monday. You specify your program that you want to run, and then launch the command, and then lots of stuff gets printed out, and I have some examples of that. So if you enter liquid perf counter with no args, here's the help message. And I'm not going to march through this, but you can look at this and get a sense of what's going on. The previous slide that I had up was an attempt to do something nice for you and kind of summarize this information. Okay, so let me give you some examples. So liquid-perf counter -a. If you run this from the command line, it just simply displays the list of counter groups that are available on the platform. You'll probably want to do this and see what's available. Liquid-perf counter -g mem a.out. And so here I'm saying I want to configure and collect data from the mem counter group. It's going to run a.out and then print out the results. So it's going to print out the counter values from the mem counter group. And I'm going to show you what output from that looks like. Building on the previous example, now I'm going to run a.out on 2 threads. And the capital N :0-1 says pin threads, pin the 2 threads to these 2 cores in this way. If I had said, I could say, if I wanted to run like 4-way parallel, I could say, -C N :0-3. And that would mean, pin onto core 0, 1, 2, 3. If I wanted to do a different thread to core mapping, I could say 0, 7, 14, 21, etc. I mean, you can do all sorts of crazy stuff if you want, and there may be advantages to doing that. And then finally, to activate the liquid marker API, you add a -M to the command line, and then what that will do is it will limit the hardware performance counter collection and reporting only to the region of code that you've marked out. So here's an example from the Liquid guys about what the output looks like. So liquid perf counter -G L2. So we're looking at the L2 cache group, and he's doing a particular type of core mapping here and running a.out. And so this is sort of the format that you see output. You see information about the processor. You'll see program output here, which has been omitted for brevity. And then you see information about the row. Each row is a different measure, and the columns are the different cores, right? And so if you run 20-way parallel, you're going to have 20 columns of stuff. If you run, you can see how this can get out of hand pretty quickly. So some of these counters are always measured. So the number of instructions, the number of clocks, and then below them are the counters that you've asked for. They get configured and reported. And then down below are derived metrics, metrics that are derived from the actual counters themselves. So this is actually an important thing to keep in mind. So in parts of this output, you see raw hardware counter data. That's the stuff up here. And down below, you're seeing derived values. You're seeing numbers that are derived from the hardware performance counters themselves. And there's a ton of information that you have to, look up to see how these things are computed. Often, just looking at the names of these things, it can be kind of confusing and it can be misleading. And so you have to be really careful when you're looking at this stuff to chase down the information and make sure you understand exactly what it is that it's saying. Believe me, I've made plenty of mistakes over the years, misreading this stuff.
So, Professor, quick question.
Yeah.
Do the counter groups, do those map pretty much directly to the components in the memory architecture, or can you access that one, the memory thing that rules them all, or how does that map out?
Yeah, so there's like a counter group for L1 cache and a counter group for L2 cache, and on processors that have it, L3 cache on Corey has MCDRAM, and so there's a processor counter group for that. There's you can count flops. There's a ton of stuff. And so on Corey, if you do liquid perf counter -A, you get a list of 15 things. And on other processors, it's more. And on other processors, it's less. So. So I know that you're dying to. Sorry, another question.
Question.
Yeah.
So are these statistics for the whole program, or we can we can evaluate a section?
Right. Yeah. So good question. So this particular example is for the entire program, and the marker API is what I was talking about, that you would use the marker API to, mark out a section of code. Say, start here, stop here, sort of like you did with ChronoTimer. But instead of using ChronoTimer, you'd use the Liquid Marker API. And then when you run this command with one additional command line argument, then you get this kind of data for just that chunk of code inside your program.
Gotcha.
Yeah. So it takes a little bit of work. Okay. So let's go back to homework 1 for a second. So, we know that the vector sum runs a lot more quickly than the indirect thing, but the question is why? And so the hypothesis was that the vector sum makes better use of the memory hierarchy. So let's test this hypothesis and gather the hardware performance counter information about memory system utilization and talk about the results. And so here's the methodology. I ran liquid perf counter. I'm looking at the HBM cache counter group on a Core EK&L node, and I'm mapping it to core 0 and the name of the program, and then there's the problem size. Okay, so I launched that, and what happened? Well, I get a bunch of stuff, and this is the tail end of it. And so first of all, these are metrics. These are derived metrics. These are not the actual counters. I'll show you the actual counters in a second. So let's start at the top here. So runtime. So we know from homework 1 that the vector code runs a heck of a lot faster than the indirect code. So we see confirmation of that here. So this process of using hardware performance counters, sometimes you know what you're looking for and you're seeking confirmation. And then other times you're going on a fishing expedition because you're not sure. And it's important to be aware of which mode you're in. You know what you're looking for. It's a very analytical sort of thing. Or are you going fishing to find stuff? Okay. So, here we see that the vector sum runs about 9 times faster than the indirect sum, just looking at the time. And so FYI, the timing information that my program prints out with using ChronoTimer is about the same. So let's look at DDR memory bandwidth. So here we see that the vector code is getting it's using more memory bandwidth than the indirect code, but remember it ran nine times faster, but we're only using 25% more bandwidth. So I'm not sure that that really accounts for anything. This is inconclusive. It's interesting, but it's inconclusive. But if we look at MCDRAM bandwidth, this looks a lot more interesting. And so remember, MCDRAM is the local high-speed cache. There's 16 gigabytes of local high-speed cache attached to each of these processors. It's not L3 cache. It's MCDRAM cache. It's external. And so here we see that the vector unit uses about 8 times the bandwidth of the indirect thing. And so I'd say this is probably a pretty good smoking gun that shows, that the vector or the indirect code is just making really poor use of the memory subsystem because it can't move stuff in and out quickly enough. Move stuff in. It's not moving anything out. It's only reading stuff in. So this would account for most of the 9x speed difference. And if I was doing a paper that I was going to submit to a workshop or a conference or something, I would go with this. This is pretty good. And so, there's strong relationship between NCDRAM and the elapsed time. So, close enough. Oh, so some of you might have noticed that there's 2 different runtime numbers here. Runtime RDTSC and runtime unhalted. The one that you want to look at is the RDTSC. This is like, elapsed time. This lower one is kind of complicated to explain, but it's it's a function. Remember, it's a metric, right? It's a function of the actual number of clock ticks that went by, modified by the CPU frequency. And so you can have the CPU frequency actually drifts over the course of time. It does. We have best answer I can give you really is that for these really short runs, I really don't have a lot of faith in the numbers that I'm seeing. And it's not until the runs last for a longer amount of time that we're actually exercising the system enough to begin to see things stabilize out. And so the fact that these numbers are so different doesn't trouble me at all. The one that you should be looking at is this one, runtime RDTSC. And when you run in parallel, you can actually get per thread runtime, which is really cool. So you don't have to instrument every single thread. You just use Liquid, and it reports it for you.
Weird.
So on Cori, remember, so each of these tiles has 2 cores on it. Each core has its own L1 cache. Each tile has a shared L2 cache. And then outside the chip is 16 gigabytes of MCD RAM spread over 16 channels, right? So this is like super high bandwidth memory. And the way that it's configured, there's 3 different ways to configure it. But the default configuration and what we've been using, MCD RAM becomes like a big L3 cache on the chip. So it just looks like last level cache. And it's shared by all cores. Okay, so let's dig in a little bit more. Homework 1. So when I am using this HBM cache performance counter, I get some actual metrics or actual hardware counters out now. And so here I'm looking at the number of instructions that were executed. And so the vector code's on the left and the indirect code's on the right. And so there's like a huge number of the indirect code's executing 47 times more instructions than the vector code. 47 times more, right? So why is that, right? So in your C++ code, there may be 2x more instructions, but not 47. So what's going on? So it's probably the case that this is the overhead of the non-sequential memory accesses that results in so many additional instructions, right? Down at the assembler level, you can, the compiler is going to say, oh, this code's going to be like, grabbing, sequential chunks of memory one after the other. And so I'm just going to grab like, 2K of them at a time, right? And so with one instruction, it can load 2K values, right? It uses, what's known as direct memory access. And this is a special microcode instruction for doing that sort of thing versus loading in one at a time, right? And so this is probably the source of those differences in instruction counts. So some comments about all this stuff. So the runtime, the sum vector is 9 times faster than the indirect one. The MCD RAM bandwidth is about 8 times higher on the vector compared to the indirect. And so when the bandwidth's higher, it means that more values are being read in per unit of time, right? That's one way to think about it. And so, as I mentioned, sum vector uses predictable access pattern that's very friendly to memory access. And so the latency associated with those in-memory accesses is reduced by a combination of the access pattern and effective use of the cache and fewer number of instructions to load it, and so on and so forth. Some indirect uses completely random access pattern. And so that latency, you can't, every memory access has a tax, a latency tax associated with it. So bandwidth numbers are just going to be awful. Because this is a small problem, it's only about 76 megabytes. So if you multiply that number times 8, because I was using 8-bit ints, it fits easily within MCD RAM. And so those numbers that we saw for memory bandwidth to memory doesn't mean anything because this problem never really touched memory. I'm not sure where those numbers came from. So main memory latency of bandwidth isn't really a factor in this problem, but MCD RAM latency and bandwidth is very much a factor in this problem. So knowing something about your problem size and the machine architecture is very useful to help you in doing diagnosis and analysis of performance when you start digging into things at this level. Okay, so potential next steps for homework 1. Well, so we know that some indirect executes 47x more instructions than some vector, but its cycles per instruction is a lot lower. right? So that's if you multiply out those two things, um, and come up with a figure of cycles, the sum indirect is only 28 and a half times more cycles than sum vector. So what are those instructions? Well, so we'd have to look at the assembler, and we'd hop over to Godbolt and drop the assembler in and see what happens. But as I said, I think it's the difference between doing large bytes using DMA transfers versus one load at a time. Another next step would be to look at L1 and L2 cache data. And so how often are reads satisfied by L1 and L2? That's something that you can figure out from looking at hardware performance counter data. And how does that change with problem size, right? So you could probably get smoking gun evidence of when problem size changed from one end to the next, that all of a sudden your L1 cache utilization rates dropped off significantly. You could find that with performance counter data studies. But we're not going to do this for homework one. But you might think about these as potential steps for your future homeworks in your project. And so one of the reasons I'm talking about all this stuff today is because you're sitting around thinking about your projects. And I want you to see what kinds of things you can do with hardware performance counters and its analysis. Okay, so homework 4 is OpenMP parallel matrix multiply, right? And so you got to start with homework 2. And so the basic matrix multiply is going to become basic matrix multiply in parallel using OpenMP. And then the blocked version is going to, with the copy optimization, becomes parallel also with OpenMP. And so the key design questions to think about is, where's the parallel work in both, and how are you going to parallelize them? And the hint really is you're going to parallelize over the output domain. So what performance measures are you going to use here? Well, so you have elapsed time, but this is just sort of start finish. And with Liquid, you can actually get out per core, per thread timing. But and so what we'll be looking for with per thread timing is maybe load imbalance, right? So we expect matrix multiply to be pretty load balanced. I mean, we have nice even problem sizes and block sizes and that sort of thing, but depending on concurrency level, there may be configurations where one thread has a little bit more, a little bit less work than the others, right? So for the hardware performance counters, you're going to need to do some exploration. You're going to have to run a bunch of different configurations with Liquid Perf Counter and start hunting. Right, this is part of the process. And so I gave you a thought process from homework 1, and you can morph that into a thought process for homework 2 about what's your hypothesis for performance characteristics that you see, and how are you going to verify that and validate it. And so in your analysis and write-up, you're going to use both the elapsed time and interesting hardware performance counter data. Okay, so important dates for homework 2. So I'm going to try and get the thing posted in the next day or two. You'll have about 10 days to work on it, and then we'll do presentations on the 6th. These dates might slip 1 or 2, but hopefully not. And the timing of this overlaps with your proposal. And you might be thinking, oh my God, and this is purposeful. So many of you are doing coding projects and you intend to do performance analysis. And so this homework is going to give you tools that you need to do that kind of analysis. So this is actually going to be helpful for you as you work on your proposal. So how much work is it? So these are my guesses. So updating your homework code to be parallel, not much time. Doing the performance runs and looking at and making sense of the performance counter data, this could take a while. This could take a while. And then once you have the performance data that you think supports your hypothesis, and you can tell a story, then writing it up, this only takes a few hours. And so the white rabbit looking at the clock here, this you don't want to delay getting started on this. You need to get moving on it right away. Okay, so let me stop there. I'm gonna give you some tips and tools you're going to need in OpenMP to make this work. But let me stop and see if there's any questions about homework 4 at this point, given what you know. Okay, so here's some
I've got a quick question.
Yeah.
Speaking of rabbits, how will we know if we're going down a rabbit hole and just spinning our wheels?
Yeah, that's a good question. So the thing is that you got to start with a hypothesis, right? And so the hypothesis might be, well, I think that blocked makes better use of the memory hierarchy, and that explains its performance differences compared to the basic one. Well, so how are you going to measure that?
By looking at usage of like the MACD RAM, CD RAM, I guess, or maybe like where it spills over to L1 cache.
Yeah. And so there's a looking at MC DRAM bandwidth is useful when the problem is larger than L2, but smaller than larger than L2 is smaller than MC DRAM. And so you might think about starting to look for bandwidth utilization between the caches, right? So how much bandwidth to and from the L2 cache, right? Because that indicates how much is not being satisfied by L1, for example, right? So think about it that way. Here in the comment, there is no L3 on the KNL chip. And so you would start there and look at the performance data from some runs and think, well, gee, is this giving me useful information? Do I get confirmation of some feature that I'm looking for? And the answer might be yes, and the answer might be no. And if the answer is no, you might want to you're going to have to dig into it a little bit and figure out if it doesn't, why not, right? Maybe you're not looking at the right thing. So, for example, here's an example. If you're looking at MCDRAM, let's say the problem's really small. You're looking at MCDRAM, and bandwidth to and from MCDRAM is inconclusive, right? And you're working with a small problem, then maybe you need to look at a different counter. You might want to look at bandwidth, L2 bandwidth.
Right. Yeah, I guess just that there's 15 different counters, and we're not familiar with them, so it's like it might feel like taking a shot in the dark at like, well, I'm not really sure which counter we're looking at or what it does.
That's fair.
Yeah,
that's fair. Okay. All right, so let's put a pin in that, and that's a excellent question. We'll come back to it because. On the one hand, spinning your wheels a little bit, it's part of the learning process, but then on the other hand, it can go on for too long, and we don't want it to go on too long. Yeah. Okay, so here's some, are there any other questions about homework 4 before I move on? Okay, so here's a few OpenMP things that you're going to need probably for homework 4. And so one is creating and using thread local storage. and the others, using multiple nested pragmas in your design. And so these two things work hand in hand in the same way that tiling and copy optimizations work together hand in hand. So why and when do you need thread local storage? So recall, we're thinking about this in terms of each thread working on its own portion of the output domain. And so for for writes from your program, the computations that you do, you're going to want thread local storage to hold the results of those local computations, which are then later written into global output. And so this is going to avoid this false sharing thing where, even though the two threads may be writing to different memory locations, so like adjacent array locations, when they do that, that actually causes some, that's known as false sharing, and it causes some cache line sloshing back and forth between those two cores, and it's going to slow down your performance. And so the intention here of thread local storage is to promote use of L1 and L2 cache as much as possible. And on the read side, the thread local storage for block and copy optimization is how you're going to make use of the cache. That's how it works. And so the design tip for you all is, your parallel code designs should nearly always include some aspect of thread local storage as an integral part of the approach. You should just be thinking about that as you think parallel thoughts. So let me talk a little bit about the data environment in OpenMP, and this is a precursor to the thread local storage point that I'm trying to make. So in OpenMP, it's a shared memory programming model, which means that most variables are shared by default. And so global variables are shared by all threads. And then not everything is shared. So, stack variables, the things you get put on the stack when you call a function or something, those are all private when you invoke those functions from parallel regions. And then automatic variables within a statement block are private. So I'll show you some examples of that. So here's a data sharing example. So we have two chunks of code. We have a main, and then we have a function work. And so inside main, we have this A array, and then inside main, we have index, and then we have this parallel section where we're going to call work, and we're going to pass in index to work, and then we print something out. And so over on the other side, this is a different file, I guess. So we're referring to this extern A, right? So it's probably referring to that one. And then we have this pointer to index that we pass in. We have this variable temp inside the function, and we have this static int count, right? And so the question is, which are global and which are shared, right? And so this diagram here shows that before we go parallel, so A index and count exist here, whereas count, right? Count exists because it's a static buried inside this function. Yes, this is horrible coding style. You would never want to do this, but for this example, it's intended to give you a headache, and so it does. So A index and count are global variables, and then when we go parallel, the only thing that's private and local is this temp variable, and it was created, right? So we went parallel, we invoked work in parallel, and inside each work creates its own thread local storage. This is an automatic variable that it's creating here, right? So, and then when the parallel section ends, then temp goes away, and we're left with the 3 that we had to begin with. So there's some things that you can do in OpenMP that are helpful, right? So you can have this pragma where you create a private variable. This is private to each thread. And so you're saying you're creating a private variable named temp for this thread, but just in this form right here, temp is not initialized to anything. And so you're using temp in an uninitialized fashion, right? So before you go parallel, temp is 0. That initialization does not carry through the private clause into the parallel section of code. And then when you exit the parallel section of code is only the loop here. Temp reverts to whatever its value was before the code went parallel. This is maybe not the best design choice on the part of the NPI or OpenMP people, but it is what it is. I want you to make you aware of this, so that this could be a potential landmine that you inadvertently step on. So what you can do is, with regard to the initialization part, is to, here I'm using the same motif, but I'm saying first private rather than private, and I'm creating a private variable increment, which I'm initializing to the value of increment in the code, prior to going parallel, right? And so each thread's going to get its own copy of increment, which was initialized to 0. There's a handful of other things like this, but these are the two most relevant ones to the thing that you might be working on. So in terms of nested pragmas, so I love this slide. This shows that these two expressions are actually equivalent. So let's start with the one over on the right. So what does this do? Pragma OpenMP parallel for. This is creating a parallel region of code. We have this for loop, which is going to be done in parallel. Okay, that's great. But what if we did something a little bit different, and we say Pragma OpenMP parallel, and we have these curly braces which indicate a block of code. So inside this block of code, all of that's parallel. All of that's parallel. And then inside that block of parallel code, we have this Pragma OpenMP4. And this does not create a new parallel region. It just uses the existing parallel region because we've dropped the parallel keyword from this Pragma. What would happen if we had made a mistake and said Pragma parallel OpenMP4? Well, then we'd have some nested parallelism going on, and that's probably not a good thing. That's probably not what you want. So this kind of construct here, where you can say Pragma OpenMP parallel and have a code block, and then inside that code block, which is parallel, you can have a for loop, which is implicitly parallel. This is a pretty handy sort of thing, because what you can do is you can create some thread local storage between the start of this code block and the parallel loop. And for example, I might create a local buffer here for my block, right? So hopefully the light bulbs are starting to go off for you as to why this is important. Okay, so another trick that can come in pretty handy. Let's say that you have two for loops, right? If we say Pragma OpenMP parallel for, that only gets the for loop right after the Pragma. But what if we got a whole pile of for loops and we want to parallelize all of them? Well, you use this collapse keyword, and here we're saying parallelize these for loops down through two levels. And so this could be a pretty handy thing to do too. But there's some constraints, right? You need to have strictly regular rectangular loops. You can't have loops that one is completely linear and then one's ragged and kind of unpredictable. That won't work. So what problem can you think of that you might be working on that has a loop structure like this? Hopefully a light bulb's going off for you. Okay, so that's it for today. So let me stop the share and see if there's any questions before we scatter. I'm going to make note of Mr. Huber's question about how to not get stuck spinning your wheels. Okay, so in case it wasn't obvious, you got to use NERSC for the next assignment, unless you want to go to the bother of trying to install Liquid on your machine and get it working, which you're welcome to do if you have a Linux machine. I don't mind, but it can be tricky, and I'm not